Hello friends, in the previous lecture we learnt that the performance of a refrigerator and a heat pump is expressed in the terms of the coefficient of performance. Then we discussed the Kelvin-Planck and the Clausius statements concerning the second law of thermodynamics, and finally learnt that any device that violates the first or the second law of thermodynamics is called a perpetual motion machine. In today's lecture, we shall be discussing the reversible and irreversible processes and the Carnot cycle. Reversible and irreversible processes. The second law of thermodynamics states that no heat engine can have an efficiency of 100%. Then you may ask, what is the highest efficiency that a heat engine can possibly have? Before we together answer this question, we need to define an idealized process first, which is called the reversible process. The process that we discussed earlier occurred in a certain direction. Once having taken place, these processes cannot reverse themselves spontaneously and restore the system to its initial state. For this reason, they are classified as irreversible processes. For example, once a cup of hot coffee cools off, it will not heat up by retrieving the heat it lost to the surroundings. If at all it could, the surroundings as well as the system, that is the coffee, would be restored to the original condition, and this would be a reversible process. A reversible process is defined as the process that can be reversed without leaving any trace on the surroundings. That is, both the system and the surroundings are returned to their initial states at the end of the reverse process. This is possible only if the net heat and net work exchange between the system and the surroundings is 0 for a combined process. Processes that are not reversible are called irreversible processes. It should be pointed out that a system can be restored to its initial state following a process, regardless of whether the process is reversible or irreversible. But for reversible processes, this restoration is made without leaving any net change on the surroundings, whereas for irreversible processes, the surroundings usually do some work on the system and therefore does not return to their original state. Reversible processes actually do not occur in nature. They are merely idealizations of actual processes. Reversible processes can be approximated by actual devices, but they can never be achieved. That is, all the processes occurring in nature are irreversible. Now you may be wondering why we are bothered with such fictitious processes. There are two reasons. First, they are easy to analyze. Since a system passes through a series of equilibrium states during a irreversible process. Second, they serve as idealized models to which actual processes can be compared. Engineers are interested in reversible processes because work producing devices such as car engines and gas or steam turbines deliver the most work, and work consuming devices such as compressors, fans and pumps consume the least work when reversible processes are used instead of irreversible ones. Reversible processes can be viewed as theoretical limits for the corresponding irreversible ones. Some processes are more irreversible than others. We may never be able to have a reversible process, but we can certainly approach it. The concept of reversible processes lead to the definition of the second law, efficiency for actual processes, which is the degree of approximation to the corresponding reversible process. This enables us to compare the performance of different devices that are designed to do the same task on the basis of their efficiencies. The better the design, the lower the irreversibility and the higher the second law efficiency. Irreversibilities. The factors that cause a process to be irreversible are called irreversibilities. They include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solids, and chemical reactions. The presence of any of these effects renders a process irreversible. A reversible process involves none of these. Friction is a familiar form of irreversibility associated with bodies in motion. When two bodies in contact are forced to move relative to each other, a friction force that opposes the motion develops at the interface of these two bodies, and some work is needed to overcome this friction force. The energy supplied as work is eventually converted to heat during the process and is transferred to the bodies in contact, as evidenced by the temperature rise at the interface. When the direction of the motion is reversed, the bodies are restored to their original position, but the interface does not cool and heat is not converted back to work. Instead, more of the work is converted to heat while overcoming these friction forces that also oppose the reverse motion. Since the system, that is, the moving bodies and the surroundings, cannot be returned to their original states, this process is irreversible. Therefore, any process that involves friction is irreversible. The larger the friction forces involved, the more irreversible the process is. Another example of irreversibility is the unrestrained expansion of a gas separated from a vacuum by membrane. When the membrane is ruptured, the gas fills the entire tank. The only way to restore the system to its original state is to compress it to initial volume while transferring heat from the gas until it reaches its initial temperature. From the conservation of energy considerations, it can easily be shown that the amount of heat transferred from the gas equals the amount of work done on the gas by the surroundings. The restoration of the surroundings involves conversion of this heat completely to work, which would violate the second law. Therefore, unrestrained expansion of a gas is an irreversible process. A third form of irreversibility familiar to us all is heat transfer through a finite temperature difference. Consider a can of cold soda left in a warm room. Heat is transferred from the warmer room air to the cooler soda. The only way this process can be reversed and the soda restored to its original temperature is to provide a refrigeration, which requires some work input. At the end of the reverse process, the soda will be restored to its initial state, but the surroundings will not be. The internal energy of the surroundings will increase by an amount equal in magnitude to the work supplied to the refrigerator. The restoration of the surroundings to the initial state can be done only by converting this excess internal energy completely to work, which is impossible to do without violating the second law. Since only the system, not both the system and the surroundings, can be restored to its initial condition, heat transfer through a finite temperature difference is an irreversible process. Internally reversible processes. A typical process involves interactions between a system and its surroundings, and a reversible process involves no irreversibilities associated with either of them. A process is called internally reversible if no irreversibilities occur within the boundaries of the system during the process. During an internally reversible process, a system proceeds through a series of equilibrium states, and when the process is reversed, the system passes through exactly the same equilibrium states while returning to its initial state. That is, the paths of the forward and reverse processes coincide for an internally reversible process. The quasi-equilibrium process is an example of an internally reversible process. Externally reversible process. A process is called externally reversible if no irreversibilities occur outside the system boundaries during the process. Heat transfer between a reservoir and a system is an externally reversible process if the outer surface of the system is at the temperature of the reservoir. A process is called totally reversible or simply reversible if it involves no irreversibilities within the system or its surroundings. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effects. As an example, consider the transfer of heat to two identical systems that are undergoing a constant pressure phase change process. Both processes are internally reversible since both take place isothermally and both pass through exactly the same equilibrium states. The first process shown is extremely reversible also, since heat transfer for this process takes place through an infinitesimal temperature difference dT. The second process, however, is extremely irreversible, since it involves heat transfer through a finite temperature difference delta T. The Carnot cycle. Probably the best known reversible cycle is the Carnot cycle, first proposed in 1824 by French engineer Sadi Carnot. The theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. The Carnot cycle is composed of four reversible processes, two isothermal and two adiabatic, and it can be executed either in a closed or a steady flow system. Consider a closed system that consists of a gas contained in an adiabatic piston cylinder device. The insulation of the cylinder head is such that it may be removed to bring the cylinder into contact with reservoirs to provide heat transfer. The four reversible processes that make up the Carnot cycle are reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, and reversible adiabatic compression. Reversible isothermal expansion with Th is equal to constant. Initially, the temperature of the gas is Th and the cylinder head is in close contact with the source at temperature Th. The gas is allowed to expand slowly, doing work on the surroundings. As the gas expands, the temperature of the gas tends to decrease. But as soon as the temperature drops by an infinitesimal amount dT, some heat is transferred from the reservoir into the gas, raising the gas temperature to Th. Thus, the gas temperature is kept constant at Th. Since the temperature difference between the gas and the reservoir never exceeds a differential amount dT, this is a reversible heat transfer process. It continues until the piston reaches position 2. The amount of total heat transferred to the gas during this process is QH. Reversible adiabatic expansion. Temperature drops from Th to TL. At state 2, The reservoir that was in contact with the cylinder head is removed and replaced by insulation so that the system becomes adiabatic. The gas continues to expand slowly, doing work on the surroundings until its temperature drops from Th to Tl. The piston is assumed to be frictionless and the process to be quasi-equilibrium. So, the process is reversible as well as adiabatic. Reversible isothermal compression at Tl is equal to constant. At state 3, the insulation at the cylinder head is removed and the cylinder is brought into contact with the sink at temperature Tl. Now, the piston is pushed inward by an external force, doing work on the gas. As the gas is compressed, its temperature tends to rise, but as soon as it rises by an infinitesimal amount dt, heat is transferred from the gas to sink, causing the gas temperature to drop to Tl. Thus, the gas temperature remains constant at Tl. Since the temperature difference between the gas and the sink never exceeds a differential amount dt, this is a reversible heat transfer process. It continues until the piston reaches state 4. The amount of heat rejected from the gas during this process is QL. Reversible adiabatic compression. Temperature rises from TL to TH. State 4 is such that when the low temperature reservoir is removed, the insulation is put back on the cylinder head and the gas is compressed in a reversible manner. The gas returns to its initial state, that is state 1. The temperature rises from TL to TH during this reversible adiabatic compression process, which completes a cycle. Remembering that on a PV diagram, the area under the process curve represents the boundary work for quasi-equilibrium processes, we see that the area under curve 1, 2, 3 is the work done by the gas during the expansion part of the cycle, and the area under curve 3, 4, 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the path of the cycle is the difference between these two and represents the net work done during the cycle. Notice that if we acted tightly and compressed the gas at state 3 adiabatically instead of isothermally in an effort to save QL, we would end up back at state 2, retracing the process path 3-2. By doing so, we would save QL, but we would not be able to obtain any net work output from this engine. This illustrates once more the necessity of a heat engine exchanging heat with at least two reservoirs at different temperatures to operate in a cycle and produce net amount of work. The Carnot cycle can also be executed in a steady flow system. Being a reversible cycle, the Carnot cycle is the most efficient cycle operating between two specified temperature limits. Even though the Carnot cycle cannot be achieved in reality, the efficiency of actual cycles can be improved by attempting to approximate the Carnot cycle more closely. The reversed Carnot cycle. The Carnot heat engine cycle just described is a totally reversible cycle. Therefore, all the processes that comprise it can be reversed. So, it becomes the case of Carnot refrigeration cycle. This time the cycle remains exactly the same, except that the directions of any heat and work interactions are reversed. Heat in the amount of QL is absorbed from the low temperature reservoir. Heat in the amount of QL is rejected to a high temperature reservoir and a work input of W net in is required to accomplish all this. The PV diagram of the reversed Carnot cycle is the same as the one for the Carnot cycle, except that the directions of the processes are reversed. So friends, here we come to the end of our discussion, and therefore we sum up. A process is said to be reversible if both the system and the surroundings can be restored to their original conditions. Any other process is irreversible. The effects such as friction, non-quasi-equilibrium expansion or compression, and heat transfer through a finite temperature difference renders a process irreversible and are called irreversibilities. The Carnot cycle is a reversible cycle that is composed of 4 reversible processes, 2 isothermal and 2 adiabatic. So that is it for today. In the next lecture, we shall be discussing more about Carnot cycle. Thank you very much.